I am. Did
Cool. And let's see. We should
we'll just
be
wait a few
a
minutes.
few seconds. Yeah. Let me just check. Normally. Okay. To refresh the page. Takes a few seconds and then it goes. Yep. I think we are live.
Mm-hmm.
It says, yeah. All right, wonderful guys. We are live. And I hope you guys enjoyed our last webinar. There were so much, people were asking so many questions. There were so many, inquisitive folks looking into what we are actually building, that we decided to make it a bi-weekly webinar. And in a bi-weekly webinar, where we want to try to give you guys sort of more of our awesome work that we've been doing, and hopefully in the next couple of months you will have a whole collection of wonderful sort of work that we have spent years building and developing. And that's the whole idea, right? I mean, what we are trying to share is, it took us like 3-4 years to kind of build this whole AI practice for energy and conventional energy like oil, gas, etc., but also alternative energy. It all takes time to sort of gain that understanding, even if you're domain experts, which is what Tannistha and Quamer are. And we thought that, squeezing it into just a few weeks, and perhaps half a year, and giving you guys all the knowledge that we have been able to acquire through hard work, makes your life easier when you want to do better and bigger things than us. So that's actually the goal. And then I think Tanishta and Kwamar will sort of recap and give you a bit of a sort of a rundown. So I'm
Mm-hmm.
going to be here, guys. I want to help you, facilitate you. So you can ask questions. We will try to answer all the questions. This is an awesome sort of a deep learning webinar where we go into code walkthrough today. So I'm super excited actually. So I can learn again things if I may have forgotten. So it's going to be beneficial for all of us. Go ahead, guys.
Yeah,
Super
thanks,
excited.
Terry. So we'll take over from here. Probably let's just recap a little bit. So the first webinar we actually talk about what's the scope of this webinar, and we also went through a few trivia questions, and people gave right answers and wrong answers, but it was very fun and enjoyable to have that webinar. um, I can probably just share my screen and what also just remind everyone that everything that you'll be seeing here, like the code walkthrough, the presentation, even this live live telecast, everything will be available in the GitHub repo. We Let me just share my screen and take you there. So this is our repo. And we did from the last couple of, like, if there is some more addition happened here for in terms of the from the first webinar. So we did put a notebook. It's the presentation for week 1 is updated here. And also some util functions and all that Kwame will be talking about. So also we modified our readme page a bit. Whenever if you want to go to the recording, you can just click this YouTube button. This is for the webinar 1, where we did overall understanding of how AI is applied to energy industry, and then we talked about the use case of geoscience. And today we'll actually go deeper into building that model of geoscience. It start with the data. So this is also what will happen for today's webinar. And so we'll keep adding these presentation links, the notebook links, and also this recording to this GitHub page. So please check back time again, and we'll also announce whenever we're adding this. So you can just keep updated with whatever we are adding. So maybe then I will start with today's presentation. me go back and share my screen for today's presentation. So today's presentation is mainly talking about the use case, which is a well-to-well correlation. Never mind if you don't know what is well-to-well correlation, doesn't matter. We'll be actually talking about all things deep learning, so don't worry about it. No fancy terms in geology will be used here. It's just how the data set is, and then we'll try to walk you through how you can build a model through it. Okay. So we'll talk about creating a good data set from a limited subsurface data. So limited in the sense it's really small. Like if you are talking about these days, it's all about a language model and all, right? So they have a lot of data to train on. But when you come into these subsurface problems, there's limited data because it takes a lot of time for like experts to annotate this data, and which doesn't happen. Many a times the annotation is also not right. So you do have to choose the data from, like, clean the data, maybe remove those annotations which are not right, incomplete, and things like that. And after doing everything, you are actually left with the limited data. So the agenda today is we'll do a code walkthrough, how to create a good data set from this limited data that Quamer will take over. Before that, I'll give some information or some like kind of understanding around the opportunities of limited data, a very high overview of MLOps framework. In course of our lecture, we'll try to introduce more of MLOps, but for today, I'll just give a high level blueprint diagram that we'll be using in DivCover more often. Then I'll talk about data augmentation techniques, some data augmentation techniques. These are not that we will walk through, but I'll just give you a link to where you can find these augmentation techniques and you can practice by yourself. And the fourth is, of course, the IPython notebook walkthrough that Kwamil will give. So as always, I like to begin a little bit about why is it important, the business side of the problems. So this is taken from a lecture that Andrew Ng gave, I think, in a Data IQ meet sometime last year. And I really like this image because here, if you see that if you actually kind of categorize all the projects, the AI projects according to value, you have a head and then there is a long tail of projects. And what happens in the head, you can have projects like web search, e-commerce customization, like getting more customers, recommendation system, ad recommendation system, even like language models can come into the head of this graph. It's because it puts a lot of value to AI models, and then at the lower tail, and also to understand that you have a lot of data, good data, level data to work on, so you can have really good recipes to work on these kind of problems. However, if you go to the long tail, as you can see, there are a few examples, like maybe this is from a manufacturing industry or a pharmaceutical industry, where you're trying to manufacture a pill and it might have defects, right? So how do you identify those defects? Then could be a steel industry, which is manufacturing some products, and there is a defect in that product. So how do you go about it? Maybe also in a semiconductor industry, how you are manufacturing those semiconductors wafers, and where is you need to inspect those. So these are a few examples of long tail projects. So these have lower values. It might be around $1 to $5 million only, compared to those huge projects at the front. But in course of time, if you think, if these things keep adding on, their total value might actually surpass all these head projects. So, but these have limited data, and there is no kind of a customized or a recipe to follow in these kind of industries. So that's the kind of problem we want to talk about in today's lecture and in the subsequent lectures, when how to work with limited data. So to give you an understanding how a limited data look like, so we Quamer will also show, and it's also there in the GitHub, a link to our data set. This is basically a CSV file that is a training set, and there's a test set. So I took first 10,000 images, and they have different well logs. So these are called well logs, which are kind of characteristics of the physical properties of Earth. These are giving information on that. But if you check, other than gamma ray, most of these other data are very sparse. Like if you pick, this is called a resistivity log. This is also a sonic log. You don't have to know all these terminologies, but I know, and so I'm just going through this. Maybe mud weight, also another kind of low resistivity. So these have really limited data here. So how do you classify this kind of sections when you have this limited data? And that's a classic example of what a long tail problem is. So here comes the data challenge. Now, I'll briefly mention a little bit about data engineering, data ingestion pipeline. So it's quite important. You build and optimize and maintain a robust data ingestion pipeline. This actually is the first step, or yeah, probably the first step of an ML ops lifecycle. I'll talk about it in the next slide. However, what do you mean when I'm talking about a data ingestion pipeline? It's like, so you have data from multiple sources. For example, today I'm showing you a data from CSV file. In course of time, we'll have LAS files, which are a different format altogether, but they have similar kind of information like the gamma ray, resistivity, and so on. Then how do you include that in your model? So that's the way you have data from different sources and you gather them together into a data warehouse or a database. Which for here we don't do that, but we actually do data ingestion pipeline and then put it in the model directly. But other than that, you can also do it like gather it in a warehouse or a database. And then you can in course of time, because the data will change, and for future proofing or your pipeline, you need to have a robust ingestion pipeline to be built, so it can handle a diversity of data. It can be costly at the beginning, but it's very important to have one of those. And it can include cleaning, transforming, merging, and more, and many more examples of this pipeline. So uh, to uh, to go to MLOps framework and to kind of bring the data engineering pipeline into this context. So what is MLOps? MLOps is actually the entire lifecycle. In very simple words, it starts from the data gathering, that goes to the model training. Then you select a model. Then you run, keep this model in model registry. Then you check the explainability, reproducibility, security of those models. And then with a CI/CD pipeline, you deploy those models, and then you kind of look at or maybe monitor those models. However, this goes to a feedback loop. It's kind of a cycle. So according to the Wikipedia, so maybe I'll just read their definition. The MLOps applies to entire life cycle from integrating with model generation, software development, life cycle, continuous integration, continuous delivery, and then it goes to orchestration, deployment, to health diagnosis, governance, and business metrics. So in order, everything included over here. So data engineering is kind of the first step, and it also is a part of this feedback loop, or maybe the entire life cycle. Um, so now it's time for a quick trivia question. So in addition to CI/CD pipeline practiced by the DevOps team, what does MLOps introduce? Like CI/CD is a practice that's been happening for a while, but what's on the top with MLOps? So is it a continuous classification, continuous regression, continuous training, or all of the above? Okay.
There are a few guys. We know. Try to see if you can answer the question, guys. It's not that rocket science. I see some of you guys are listening in. So maybe about 5 more seconds.
Yeah, and let's just have the answer. Yeah. So continuous training. Even though I can actually say it, part of classification and regression also falls in a model training. So you can also have a D also in this case. Okay, so we'll go to now we'll change the topic and go into data augmentation. So again, this is theory. However, I do think most of you know that it's a very important step to be done, and especially when you have a limited data. But why do you need a data augmentation? So it increases the models, it generalizes the model, and it also kind of minimizes the data overfitting. So these are kind of the very basic importance of data augmentation technique. It also, of course, it increases the accuracy because it's kind of minimizes the overfitting, right? But it might have a few drawbacks. You need to evaluate your quality of data augmented data sets sometimes. And there could be some bias introduced because of an augmented data set. So there are various kind of data augmentation techniques, and it depends on the type of data set you are using. So in this problem, we'll only kind of talk about image data. So this is a screenshot I've taken from a PyTorch implementation of all the data augmentation techniques. This can be center crop, color jitter, things like that. They have quite good definition of what these are. So yeah, I can actually put all these links to it. I think I have the link, but if you are interested, they have nice explanation on their page. So this is an example where they have shown a random resize crop. It's kind of a you crop a section and then kind of resize it so you can see the number of pixels kind of varying or became more pixelated or the pixel size increase, kind of things like that happening. And then there is a random color invert, so you can invert the color, change the color. It also gives more what is that, a generalization or more into the data set. This is Kira's implementation. You can run your own codes. This is taken from I put the link over here where it's just changing the position. I think, yeah, it's kind of implemented with flipping the position of the bird. This also adds variability to your data set. And then I will actually kind of talk a little bit about Augments. It's a quite a state of the art augmentation technique, which actually increases the generalization and robustness of your model. So you can have a series of different transformations applied to your original image and combine them with weights, and then you get a totally different data set. So even though it's a little bit wordy here, but the takeaway point is it improves your generalization because it's adding newer unseen data to your model. Then it improves the performance because it has a better representation of underlying data set. And one of the other important point is in case of adversarial models where you have this creates adversarial image examples where you are trying to fool a neural network into making some incorrect prediction, and then it in course of time this actually improves the robustness of the neural network or the deep learning model, and they are also more resistant to attacks, or maybe like if a totally new data comes in, then it can actually overcome that. So this is why Augments is a quite a good technique to follow. Its implementation is this is the link to the actual paper, And PyTorch has a good implementation. Also, in the same PyTorch data augmentation page, you'll have an implementation of Augments. And having said that, we'll now jump into our data set, and Kwame will talk about how limited already shown you how limited our data set is and how to um, create useful good data out of it. So before we go, I have another trivia question. Which of these techniques are useful for reducing variance or reducing overfitting? So L2 regularization, data augmentation, dropout, or all of the above? So I'll have 1 minute on this. Okay. So the answer is all of the above. Okay. So you have actually use all these techniques, and many of you might have heard of all these techniques. But today we'll be mostly focusing on data augmentation techniques. So maybe with this, I can. Oh, sorry. I do have few more slides. I'll just talk about to give you an overview of the data before Kwame takes over. So as I mentioned, this we have a CSV file, and these are all the headings. So don't worry if you don't know about it. But what we are trying to identify is based on all these well logs, we are trying to categorize the subsurface into different layers, which are called lithologies. Okay. So, and when wells are lying close to each other, they share the same kind of lithology. But in most of the time, oil industries are struggling to know what these lithologies are. So if they are trying to dig a well close to a known well where you know the lithology, they want to know beforehand what is the lithology and at what depth are you getting this lithology, because that helps you in production mostly. So if you have more fractures in that area, then it has a good productivity for that zone and things like that. These are more high level, more into geology, but that's the reason they are more interested to know about this, and it's kind of an ongoing topic now in oil and gas industry. This is just to give an example how where what is the range of these data sets. So um, actually these are all dependent on the tools they are using. So 6 to 24, this is a caliper log. It depends on the caliper tool they have used. It's also the gamma ray tool they have used. So they are all in a different, what do I say, in a different scale. So none of the scales are kind of similar, except for probably these resistivity logs might have the same tool that has measured it. Otherwise, most of these scales are also quite different. So there is quite a complexity in this data set, just to give you an idea of this too. So once again, what we are trying to achieve at the end of this model building is, if you have an unknown well, so probably you know well one and well three, and you are trying to dig or drill an unknown well. So we want to see where are these zones lying. Is it like the purple, pink, green, or yellow? Where are the zones, and at what depth are the zones? So if you know about this, you can actually know which location is best for drilling a well. So that's kind of the under, overall business case in a geology perspective. And now we'll go into the machine learning part of it. So Kwame, can you start sharing? I'll stop my
Yeah.
screen.
Okay. Hi everyone. I'm Kamal. So I'll be giving a code walkthrough of just the data preparation part. Let me share my screen. I hope you guys can see my screen. Okay. So as Tanishta mentioned that this is the repo that we will be using, and we will have all the utility functions as well as all the notebooks and all the codes present in this repo. And over here in this notebook section, we'll be having our notebook, and all the utility functions that we will be using in the notebook will be dumped over here in the utils folder. So So let's open our notebook, and you can click on this open in collab badge. And, yeah. So you can click on this open in collab badge, and then it will open it in the collab, and you can run it like right now as well. So this is basically this whole notebook is divided into 6 sections. First being like importing all the necessary libraries. Before doing that, it is necessary that you just delete all the. I mean, if you already have run this, then I would suggest that you should delete all the runtime and then restart the runtime. So this whole notebook is divided into 6 sections. I mean, obviously, the first one is importing all the necessary libraries. Then we have provided the link of the dataset, so we will be downloading that dataset. And then we have provided some dataset description as well. Then we will be doing some exploratory data analysis, and then moving forward, we will be doing some data processing, and then finally generating the dataset. So in this particular notebook, we have used this particular matplotlib library version. So it's necessary that you install this matplotlib version, and then we yes. And in order to download this data set, so basically we have provided you the uh, Google Drive link. So in order to download the data from Google Drive link, you can use this gdown library. So you need to install this as well. And then okay, so moving on. So so if you are cloning this repo and then using this, then you don't need to do this particular process. But if you running it on collab, then you need to have all these utility functions. So basically it's downloading all these utility functions and then moving it in the way the repo is structured, and then finally it's downloading. And so you can see that it is appearing, I mean, all these utility functions are appearing over here. And then and you can look into all these utility functions, and it has got all the doxing. You can reach out to us as well if you don't understand some particular what a particular function does. But it has got a rich doc string, so you can look into it as well. Okay. Moving into so these are the links that we have for the data set, so we can download this. Moving forward, so it's getting downloaded right now, and it's being saved over here in the raw data folder. So this is the data set that we are using, and it has got several, I mean, as Tanishta already mentioned this, that we have got several logs that are extracted from within the earth. So this is the data set that we will be using. And these are some of the statistics of the dataset. So the first step is to load the dataset, and I am using all the utility functions from over here. So if you want to check what those utility functions are, you can go ahead and check all these utility scripts. But right now, I'm just going to keep it high level. If you have any question, please let me know so that I can delve deeper into it as well. So we load the dataset, both the training and test set. And next, our main step is to do a exploratory data analysis. So EDA is quite important to understand how your data is, what is the quality of your data, and how you are going to proceed further. You need to see whether there are missing data available, whether I mean whether your labels are missing, or do you have some columns or features which you don't require. So basically, in order to do the data cleaning, you need to first understand what the data is. So here, this is what we are going to do. And in this particular data set, we have got this number of 1 million rows in this in 29 columns. And in the test set, we have got about 13600 rows in 27 columns. And we have got 10 unique wells in the test set, whereas 98 unique wells in the training set. So while doing the quality check of the data set, there are three major things that we are going to do. The first one is basically there is a particular column, formation column, which we don't require. So we will be removing that particular column, basically unnecessary column. And there are some scenarios where we don't have our labels, where there are, I mean, labels are missing. So we are going to impute that labels. And yeah, that's all. So let's go ahead. So first we see that what is the data set size over here, and then we see that what is the number of wells we have got in each training and testing data set. And this particular graph shows that how many, since as I already mentioned that there are 98 wells in our training wells, so we need to see that what is the number of data points that are available for a particular well. So this basically depicts that the number of rows that are there for a particular well. And similarly, this is the one for testing well. And moving forward, we want to get the names of the well from within the data set. So we again use this utility function to get the well names, and then the next step is actually quite important. We need to see that whether or not there are overlapping wells in training and testing wells. So there is a training well, and then there is a training set, and then there is a test set. So we need to make sure that there is no well that is present in both training and test set, because then it will create a bias in the, I mean, it won't give our model's performance won't be correct, because there is a bias introduced over there. The data bias will be introduced. So we need to make sure that there is no overlapping between well train and well test. And as you can see over here, that there are zero wells that are overlapping with each other. So moving forward, we want to check, I mean, if we want to get a random well and see how the data set looks like. So this is how the data set looks like. It has got all these values, and you will be noticing that there are several lands, as Tanisha showed in that in the earlier slide, that apart from gamma ray, I mean, every other column has got a numerous amount of NaN. But fortunate enough, in this particular problem statement, we don't need to do any imputation on this missing data. And the reason why is it lies on how we are going to create the data set, which I will be discussing further. So moving forward, we also want to see, basically this shows that what is the percentage of data that is missing in each column. And as you can see, apart from these few columns over here, all these columns have huge amount of missing data set. Over here, it's, I mean, this SGR is missing about 90% of the data set. And similarly over here as well. But the good thing is that in this particular problem statement, no data, I mean, you need to, I mean, it depends upon the problem statement. Sometimes in problems, in actually most of the time, missing data is a tricky one, and you need to impute this. But it also depends upon your problem statement, whether you want to fill that data or not. Because in this particular problem statement, no data is also a data for us, because it might so happen that a particular, I mean, if a drilling company is drilling something and at a particular location they couldn't drill, so there is a reason behind it that they couldn't acquire the data set. So that is also information for us. So we didn't want to include any synthetic data set over here by doing imputation. So we did not impute any data set, because in this particular problem statement, no data is also a data. So, okay. And here is basically this group identification is this, there is a column in the data set called group, and that is what we will be trying to predict. This is our label. So we are basically getting this group identity from this method group identification. We are getting the labels of our training and test set, and you can see, you can read all these documentations as well. I mean, and you can also look on this utility functions. So seeing it over here, most of the time this Horland group is almost all the time present, whereas this Stein group is, there is a data imbalance problem over here. So okay, and okay, yes. So after that, we want to see that whether or not our group information, which basically is our levels, has some missing data. And it turns out that in training data set, we have few data points where we don't have group information. But since we have already seen that, so we can just use forward fill method from the pandas library to fill all the group informations. So again, you can look into all these utility functions to know exactly what the code is. But I mean, in general, what we have did is we use this forward fill method to fill the nans in the labels. And this is just showing how the well is. It's a deviated well, but I mean, you don't need to concern, you don't need to worry about this. And here we are basically finding out which particular well has got missing values. So in our training set, we have got four wells which have got missing values, and this particular well has got 32 data points where the labels are not present. And I mean, in here it's 46, 48, and then over here is 1152. So we are going to fill this information. So up till now, it was EDA. We were trying to understand how the data is, what are the things that we need to do. I mean, basically, EDA is to plan on how do we do the data processing. So up till now, we did EDA. We got an understanding of how the data set looks like, and moving forward, we will be doing data processing. So in the data processing step, there are actually just two steps that we have, and we are actually, I would say that we are fortunate in this particular problem statement that we just have two data processing steps. Otherwise, in other different problem statements, we will be having numerous amount of data processing steps, doing imputation, removing outliers, and all this stuff. But in this particular problem statement, we don't require that. I mean, our problem statement doesn't require doing all these processing steps.
Yeah,
So
so just to add on it, we want to actually check even if there are outliers, we want to include those in our data set. Many times we remove those, but here those actually give you quite valuable information. So
exactly.
that's the reason we are taking all these nans, outliers, and every kind of value, and then just kind of running our model on it. So one thing also to note, Kwame, I don't think you mentioned. So our data set is right now in CSV. So and then we, because it's a very limited data set, and you want to create a useful data, it's very limited data. We want to create a useful data set out of it. So we are dealing this problem in terms of so computer vision model. So we are converting this into images. Okay. So you have, I think you have an image, but
Yeah, yeah. So moving forward, I mean, in the end, I
will.
showing the image.
Yeah, so this is also a way we have dealt the problem with. It's not like we just converted the data set to an image. This has like the other examples where well-to-well correlation has been done. No one tried this method before, so everyone was taking this data as it is from the tabular format and using it. But here we have converted it into a into this computer vision model, and we are try that's the reason we are preserving all the problems that we have, like the nans and outliers, to check on this data. So yeah, please go ahead. And also, I think, Kwame, this also is increasing our data set value, right? So we were
Yes.
able to get around 33,000 or maybe 4,000. We'll share this data set, the augmented data set, and the data, like the image data, with you in like in the next subsequently. but it actually was also helping us to get much more data. So that's one of the reason, also taking from other people's experiment, we think that this is a better technique to go forward. Yeah, Pamela, go ahead. Yeah.
Okay. So, I mean, as I mentioned earlier, that there are mainly two particular processing steps in this particular problem statement. But as I already mentioned, that we are fortunate enough to just have two processing steps. But I mean, in different problem statements, it depends upon the data and the problem statement. So, processing step will change in different problem statements. So here in this particular cell, we will be removing this formation column because this is not necessary, and it doesn't give us any information on the levels. So we are removing this, and over here we are basically filling the group information based on, I mean, for each well. And then we also need to check, once we have filled the group information, we want to verify that whether or not there are still some missing group information. So as it
Hmm.
turns out that we have filled all the group informations. And
Just Kramer, maybe we can just explain this image a little bit.
yeah,
Once the
yeah,
plot here, then
yes.
plot below, so it's easy to understand.
So here, so basically, essentially, this is what we are doing. This problem statement could have been approached in many different ways, but we chose to do in this way because the geology, I mean, the subject matter expert do this identification in this particular way. So this is the reason why we choose to convert this into a computer vision problem statement rather than just a regression problem or uh, classical machine learning problem statement. So if you see that there is a spike over here in this particular log, and then there is a grouping. So this is the ground truth that we have, and this is what we are trying to predict. So based on these spikes, it tells us what group or how our labels look like. So here, as you can see, that in this sonic log, there is a spike, and then it shows up over here as well that there is a change over here. Same goes for this particular area. Here is a spike, and then there is a change. I mean, and it's consistent in all these logs. Here, everywhere. So over here as well, you can see here as well. So everywhere, wherever there is a change, it is depicted in the input data that we are having. So yeah. And had we been using this in a classical machine learning approach, then it, I mean, to our eyes right now, it's very obvious that even you guys who are not subject matter expert can see and visualize that there are, if there is a spike, then then there is a change. But had this been in a CSV file or in a classical machine learning approach, you wouldn't be able to identify, even even subject matter specialists wouldn't be able to identify where the group is changing. So this particular approach is, I mean, this is the reason why we chose to use direct our approach towards this computer vision problem. So now comes the main part, basically where we are generating the data set. So this is what we, I mean, so basically we are creating this image, but not in this particular format. Instead, what we are doing, as you can see over there, that in each panel, you can see over here there are two logs, and then there are three logs over here. Hold on. Let me show you. So as you can see in this panel, then there are three logs. In this panel, there are three logs. In this panel, there are two logs and one logs. So we did not create in this particular way. Instead, what we did is we flattened out
Yeah,
all
so
this.
this is actually a way how geologists read the logs. Yeah, so as I mentioned, there's so many different scales. So they kind of group these like SP, caliper, and gamma ray into one track, and the resistivity into another. The neutron porosity, sonic, and all into different tracks. So they call this as tracks, and that's how the reading is done by geologists, because all these, when you group this way, it's easier for them to visualize it. So but we are not taking this approach here. Rather than, we'll just create simple images out of it. Yeah, go
Yes.
ahead, Coleman. Just wanted to
Okay.
add this.
So here we are again. There is a problem. Let me show you. So in this particular image, as Tanishta showed earlier, that there are several augmentation techniques such as random flipping, random cropping, color jitter, and all that stuff, which Tanishta mentioned earlier. But unfortunately, we won't be able to use all those augmentation techniques in this particular problem statement, because if we use this color jitter, or maybe if we use random crop, then basically we are, removing part of the image over here, and so is the ground truth will also be removing. So we don't want that. And as well as, I mean, if we do a posterior, if we rotate the image, then also it will basically deteriorate our model's performance, because it's, you know uh, in a way it's hindering the process of learning. So so, so basically this is so essentially we are doing three types of data generation. One is the normal way. The normal way is basically taking all these curves that I showed you and stacking side by side. And another way is randomly, basically random. So there is, I mean, if there is a curve one over here, then there is curve one, curve two, curve three, curve four. And in the random generation part, we basically mix up all these orders of this curves. Whereas what we in the other step, what we did is we inverted the whole image. So we did an upside down, so that also gives us a new data set. So let me just show you this whole image. So this is how the image looks like. So this is the whole image. So I mean, as I showed you in the previous example, all these curves were superimposed with each other. But in this particular problem, what we thought is that we will just horizontally stack all these signals, so that it is clear, more apparent as compared to that one. So in the random ordering, what we did is, maybe we took this particular
Yeah,
curve
and
and
also
we set it.
here, yes, just to add, also here it doesn't take into account the different scales we have. So because we're
Yes,
just stacking the signals, so it doesn't matter. So we are able to just not get into the complexity of those scales. Yeah, go
yes,
ahead. So yes, when you see a large farmer, can you please stay in that image? Yeah, maybe you can show that blank space.
yes.
So
So basically, these are the nans. But I mean,
yeah.
yeah, as I mentioned, that there must be some problem, or this must not be the zone of interest for the drilling company, or the company which is doing exploration. So they did not care to take the data at this particular location. But this also gives us a information that this
Mm.
particular area could be of a particular type, and that is the reason why they didn't take the data from here. So as I mentioned earlier, in
Or
this particular
probably the tool didn't work, or tool might have broken. Even
Mm.
yeah,
some kind
yeah,
of physical or mechanical
some
problems
problems.
happened in
I
that
mean,
zone. Hmm.
it either could be there could be some problem in getting the data from this particular area, or the company didn't want the data from this area. So it's basically giving us an idea that what all possibilities could be over here. So this is basically a data as well. And this is how our ground truth looks like. So it has got I mean, this is a CSV file which has got all the uh, group information at each pixel in this vertical line.
Yeah, and there is also a blank space, right, in that image. Just can you go back to that image? Just wanted to show that also.
Over here,
There's a lot of, yeah. So over here, like you in other images you'll find some presence of other signals here, but in this particular image there is a signal which is actually none, so that they didn't plot here, right?
Mhm.
So in many of these situations you see like just simply blank on that region. It's because there is no signal there at that depth. That's only the reason
as
behind it.
I mean, remember I showed you a graph that and about 90% of data was missing for SGR column. So most probably this, I mean, this column, this curve I mean, would have been for SGR column, but since almost 90% data is missing, hence there is no curve visible over here.
Mhm. Hmm.
And then finally, this is how the ground truth looks like. So that's all for this week.
We
In
can
the next week,
probably discuss the two techniques, the two augmentation technique, Kwame. Just
yeah,
Maybe
inverting, yeah.
yeah, I was just
yeah,
trying to
as I mentioned,
mind the time also a little bit. I think, do you want maybe tips and tricks? Is there any other webinar in which we will go into
Yeah, we can go
hacks and
into.
tips and
Hmm.
tricks? Perhaps that's
Yeah,
better
yeah.
because now maybe I can help summarize. So you guys have seen a full sort of a pipeline, how a single pipeline looks like. It takes a lot of back and forth, which we will add in, the tips and tricks. There are several techniques, several types of loss functions, many other different things will come. How to tweak the first exponential curve, and then there is plateauing because small data has its challenges. And Commerce has dealt with this on a regular basis. We work with international customers around the world, and there, you're hitting the ceiling with roadblocks that sometimes the data prohibits because lack of sufficient data, and sometimes you have to anyways do augmentation because you need to clean, you need to remove the NaN values, etc. Um, I think maybe it might also be a good idea for us to give you in one of the webinars a bit of a more three-dimensional view of how what are wells. You may have heard terms like wells, well logs, and resistivity logs, gamma ray, etc. It's actually quite interesting. Although I don't have any geology background, I got very fascinated with it when I was working with Tannistha and Quamer because I was learning a lot. So I was reading books. There's a lot of mathematical cool functions we use constantly to do error correction, both at statistical level, at mathematical level, and it really kind of enhances your learning. I have personally sort of learned so much from learning from these difficult domains, and I always say boring domains is where you learn the most. Fun domains is where everybody builds tools. So essentially, you're not learning; you're using. And ChatGPT is a perfect example of a fun domain in language models, but behind that also there's a science. There's a lot of hard work that has gone into making how to actually create tokenization and making sure that you're making the right prediction and having a right text generation. Similarly, in this case as well, we're learning the hard way, but it's a great, to me it's been a perfect journey, and I'm learning from my colleagues. So I guess that's my summarizing thoughts, but I will let Tanishta and Kwamar summarize. Please keep going back to our GitHub page. We'll keep refreshing it. There's going to be lots of new notebooks, and as Kwamar is already putting, Binder or perhaps straight to Colab, you can also run them. And I'm hoping that you will ask us questions as well. So I don't know, Tanisha, you want to wrap it up?
Yeah, just to wrap it up, so it's these are we just wanted to show how you can work with small data, and in subsequent webinars, we will actually take this data, the actual small data that we created with the augmented data, and we'll be using it. This will be also in the repo, and in the if you are following us on Earthscan group, we'll be posting this when we upload. I'll just put an email, like put a post over there that it's uploaded, so you can also look back into that GitHub. But this is to give, this was, I hope you got an idea how like a small data set look like, and hopefully next webinars will be able to show you how to create a good uh, model out of it.
Awesome. And for those, this is a really live session, so you can literally sort of ask us questions. Uh, it becomes very interactive. We know that recorded sessions, all these will be recorded as well. They will be on YouTube. And our platform that we are developing in the next 2, 3 weeks will have earthscan.io. platform pointing to our real website where all these webinar series will come. We will make sure that everything, the code base explanations, everything will also be there in a more explanatory format. So even if you're a layperson and do not understand much about deep learning, but are a petrochemist or geophysicist, or vice versa, that you understand a lot about machine learning, but are wanting to learn this new domain, we will do our very best to put all that information into our website. But for now, GitHub is your friend. Go there and try to look at it. You can fork it. Do keep updating your fork because eventually, it's going to be your friend as well. Um, Thank you very much, Atif, Tahir. I really appreciate that you stayed back. It's been a long session, almost close to 1 hour, and I really appreciate it. Thank you for participating. Go tell your friends, your colleagues, or any other aspiring geophysicists, geoscientists, or perhaps even managers who are looking into understanding, because I know a lot of companies are doing small or big machine learning projects. Machine learning seems like a very exotic animal. So, you tend to leave it to the techie, nerd people. But I know that many managers also started taking a lot of interest and have become, proficient in their jobs and reporting back to their business functions around the benefits of machine learning. These are all long journeys, but in the end, the payoff is also extremely sort of long term and very fascinating. So I hope you guys enjoy this. Thanks very much,
Thank
and
you.
looking
Thank
forward
you.
to seeing you guys again. Thank you, Danny. Thanks, Quamer. Once again, it was a wonderful session. Again, like I said, I learned again some more things, and I know with Quamer and Tannistha, I have so many conversations, and they're extremely bright people. Very proud to have and see my team share this with you. Thanks,
Yes, yes,
guys.
Bye.
yes.
See you guys soon
Bye.
again. In 2 weeks
Bye.
again, we're going to be back. Thank you again.